Hello, AP Calculus students. It's Mr. Ford here with another summer packet tutorial. This time we're talking about topic B, domain and range. Remember, the whole focus of the summer packet is to just make sure you check in with yourself and you are aware of what these things are. Domain and range are terms that get used a lot more in calculus than they have been in previous classes. In fact, like a lot of things, you might learn that the reason why you learned about them in other classes is so you can use them in calculus. That's often the case. So it might be worth a minute of just sliding off to the side here and talking about what domain and range are for a minute. Domain is all of the x values that you can use inside of a function. If you have some sort of function, usually we think about this thing like a machine, where you plug in some number, kind of like this, and your machine does some work and you get some number out. So what you do is you plug x's into the machine, and x is the domain. And you get values out of this, which we usually call y, or also just f of x. These are terms that we use for this. And the things that come out of the machine are the range. The range is the possible y values that we can get out of a function. Now when it comes to domain, the first 6 questions here are all asking us to state the domain of the following functions. When it comes to domain, there are probably 2 big things we should be aware of. Number 1, you are not allowed to divide by 0. If you find yourself dividing by 0, this causes there to be something missing in the domain. So rule number 1, you can't divide by 0. We'll see that pop up a couple times right away. Number 2, you cannot take the square root of a negative number. You can't root a negative, unless it's an odd numbered root. That's kind of confusing, but even numbered roots will never be negative. You can't. There's no such thing as a number that you multiply by itself and get a negative answer. It's either positive times positive or negative times negative. So those are the 2 big ones that usually show up in domain and range problems, which is what we're going to talk about right now. So let's look at this. Number 1, f of x equals 3. This is a horizontal line. We wanted to sketch a graph. It looks something like this. Now, usually with my Algebra 1 students, I use a ruler for this. With my Algebra 1 students, when we talk about domain and range, I talk about Terminator. How when Terminator enters the room, he scans the room from left to right with red vertical 90s technology lines. That's exactly how domain works. If you scan this graph from left to right, where do you touch it? Where do you touch the graph? In this case, you always touch the graph. You should be familiar with this symbol. Domain is all real numbers. You may or may not have seen that symbol before. That's what it means, all real numbers. But we're talking about interval notation here, which is what the AP Calculus test usually uses when people are reading your answers. So we should be familiar with that too. The domain here is negative infinity to infinity. And we put round parentheses around those because you cannot include infinity. Round parentheses means that you don't include it. I guess I should reuse the word don't. I'm sure we'll get a chance to talk about parentheses that you will include in a minute. But for now, interval notation usually works like this. You have A to B, where A is your left bound and B is your right bound. Or if you're going vertically, bottom to top. And then you choose to use around parentheses if you're going to not include it. I guess I already wrote this note down, but hey, these notes are getting bulky right now. Or you use a square bracket if you're going to include it. We'll get a chance to talk about this in just a moment. Let's take a look at another one. Number 2, this is a polynomial. X to the third minus x squared plus x. Polynomials are smooth, continuous curves. They never have any problems. So the domain here is also all real numbers. Or if we're using interval notation, negative infinity to positive infinity. Like that. Number 3 is the first problem we're going to run in today that does not have a domain of all real numbers. The problem here, of course, is the bottom of the fraction. You cannot divide by 0. So it might be a good idea to write down that x cannot be 0. Now, if you write down that x can't be 0, that's probably fine. The AP test is generally really generous, especially on the free response section where you have to write out your answers. The AP test is usually really generous with what they will take. But since we're practicing interval notation, let's practice interval notation. The other way to write the answer here would be all the numbers from negative infinity to 0, but not including 0. And we'll couple that with the group of numbers from 0 to infinity, again, not including either number. Usually you'll see this symbol in between them. That's an uppercase U, which stands for the word union, like that. If you go on to a college math class or something, you might see the upside down U, which is the intersection. That's unrelated to this, but there you go. Interval notation would look something like that down below. Let's take a look at number 4 while we're here. Okay, here's where we get into things that, like, if I'm assigning a summer packet, these are things that I'm looking at seeing, okay, do you know how to do this coming out of your Algebra 2 or pre-calc class or whatever. Here we have x minus 4 over x squared minus 16. What we're going to do really quick is give a quick factor to the expression on the bottom. X squared minus 16. This is what's commonly referred to as a difference of squares. You can write this as x plus 4 times x minus 4. If this is a leap for you, we will work on this year. We'll certainly see a lot of examples of this kind of thing happening. I certainly don't mean to make this class with a big wall around it that says, no, you can't get in if you don't know how to do this stuff. We will continue to practice those base skills as we learn calculus as well. But this is a good example of an algebra thing that, you know, at this stage, we're kind of thinking, okay, do you know how to do this? Because that would be kind of expected on the AP test. Of course, what's happening here is that you have 2 places on the bottom that make the denominator of this fraction 0. If x were to equal 4, or if x were to equal negative 4, if I'm drawing the arrows correctly, plugging in 4 or negative 4 makes the whole bottom of the fraction 0, and therefore you can't divide there. So there are 2 problems here. So when it comes to our domain, you could write that x is not equal to 4 or negative 4. That would be a little bit loose, though. We usually don't write it like that. If you were to write it like that, you'd put a little bracket around like this, something like that. This is usually called set notation. But again, for the 4th time, I'm going to say, okay, we're talking about interval notation today. So we're going to use all the numbers from negative infinity to negative 4, but not including negative 4. We're going to union that together with all the numbers from negative 4 to 4, not including 4. And we're going to union that with the set of numbers from 4 to infinity. This is kind of the answer that we're looking for in this particular answer. And yes, there is probably something to be said about, at this point, I'm kind of reviewing things. There is a hole in this graph at 4, and there is a vertical asymptote in this graph at negative 4, but we have another topic for that later, so we will get to that when we get to it. Let's take a look at number 5. This is, again, going to ask us to be able to factor an expression on the bottom, so you have to have some factoring skills coming in. And it's okay if you don't. We will continue to practice this. On the bottom of this fraction, you know, there's a lot of different ways to learn how to do this. I honestly, whenever I teach this in Algebra 1, I usually am like, you know, I honestly never learned a way to do it other than guessing and checking. So this is what I do. I just pick 2x and 2x and say, okay, can I find a thing that works here? I know I need to have negative 3 in these 2 slots. So minus 1, minus 3, what's going to work here? I think having... well, if it's 2x, minus 3 plus 1 would work. Yeah, minus 3 and then plus 1 would do the trick, because I get negative 6x and plus 2x. There we go. You can choose whatever factoring method you're familiar with, whatever you like. I've heard people like the slip and slide method. I've tried to learn that a couple times, but this is the guess and check is the only way I know off the top of my head. Now, what this means for us is that if x is equal to 3 over 2, or if x is equal to negative 1/2, we're going to get problems. All I'm doing there is kind of solving the quick math problems of 2x plus 1 and 2x minus 3 equals 0 in my head. That's kind of the thought bubble happening right now. That's where I got those numbers from, 3 over 2 and negative 1 over 2. So our domain in this problem is, again, all the numbers from negative infinity to negative 1/2, union together with the numbers of negative 1/2 to 3 over 2, union one more time with the numbers from 3 over 2 to infinity. This is a kind of a bulky way of saying all the numbers except for negative 1/2 and 3 over 2, but it does work. Number 6, we finally get to talk about square roots. Here, again, the thing is that this expression, whatever this is, has to be 0 or above. So a good way to think about this problem is, where is 2x minus 9 greater than or equal to 0? That's kind of the way we want to think about this. If 2x minus 9 is 0 or more, it has an answer. But as soon as 2x minus 9 dips into negative territory, we're in trouble. So we have to solve this. We'll just do the quick algebra on this one. X has to be greater than or equal to 9 over 2. This is a good example right now, too, of the level of kind of algebra steps that we usually do. It's kind of assumed that you can go from this to this. I only say this, again, I do not mean to throw up a wall around this class. I just mean to say that this would be kind of the expectation. This is the good reason why we do a summer packet like this. Anyway, with that out of the way, we kind of know that this is the domain right there. As long as x is a number that's bigger than 9 over 2 or equal to 9 over 2, we'll get a 0 or a positive number in that slot there. So our domain, you could write it in set notation and say all the x's that have an x value greater than or equal to 9 over 2. But the interval notation way that we're going to write this is a square bracket with 9 over 2, comma, infinity, round bracket inside of it. This is the way we usually write this in AP Calculus. That includes 9 over 2, because 9 over 2, it does work. It gives you 0. So there you go. Let's jump ahead down to number 7. Again, we're talking about logarithms now. So let's go back to my notes for a minute. Logarithms are a thing that you learn about usually in pre-calc, and then they do show up all over the time in calculus. Again, the way our curriculum is designed, the way that Mrs. Walter and I talk to each other and communicate, and the whole math department, we do this, everything is kind of spiraled. So you will continue to see pre-calc topics inside of calculus. If you have not mastered them yet, that's okay. Logarithms, log base x. The x in this case has to be a number greater than 0. So when it comes to logarithms, x must be greater than 0, and that's the key. You cannot do log of 0. The way I always think about logarithms, if I said the log of 0 is something, like let's say it equals some unknown x, this is a log base 10. And what we're saying is that there does exist some power where 10 to the x power is 0. If you think about the logarithmic number shuffle we're usually thinking about. This doesn't exist. You cannot raise 10 to a power and get it to equal 0. You also cannot raise 10 to a power and get it to be a negative number, negative y or something like that. So this is why the x input must be a number greater than 0, because saying log base 10 of x is saying there's some 10 to some power equals whatever that is right there. So you need to have a numbers greater than 0, because 10 to the x will only ever give you positive numbers. So with that in mind, we need x minus 10 to be greater than 0. We're going to solve this the exact same way we did the square root problem a minute ago. X minus 10 is greater than 0, which really means x has got to be greater than 10, like this. If you have a graphing calculator, side note, if you have a graphing calculator, another great way to solve these is just graph them and take a look at the graph. But we're assuming that you don't have a graphing calculator for this. So in this case, our domain is the numbers from 10 to infinity, not including either. The round bracket over here is very important on this problem. 10 is not included. And number 8, we have another factoring kind of problem that we've got to deal with, and there's a square root involved. So there are two kind of separate cases that we need to think about here. We're going to think about them separately. How about let's start with the square root of 2x plus 14. Doesn't matter what's going on in the bottom. If this doesn't exist, then it's not in our domain. So just like the other square root problem, we got to solve the problem of when does 2x plus 14, when is it greater than or equal to 0? And again, this one's pretty easy to solve. 2x is greater than or equal to negative 14. And if you divide by 2, you get x is greater than or equal to negative 7. So there's the first part. Now keep in mind, that is not the final answer, because there might be some other problems with the denominator of this fraction. So let's think about the denominator now. I'll use a highlighter here to delineate my work. So we have x squared minus 49, which, like number 4 or 5 up above, is also a difference of squares. It's a pretty simple factoring. This is x minus 7 times x plus 7, which again produces two places where there is a problem, when x equals 7 or when x equals negative 7. These are numbers we need to watch out for. So our objective here is to put all of this information that we've got together into one statement about the domain of this function. So looks like any number greater than equal to negative 7 will work for the top of the fraction, and any number besides negative 7 or 7 will work for the bottom of the fraction. There seems to be only one number that will cause problems on both the top and the bottom, and that is negative 7 itself. So for our domain, we're going to start with the number negative 7, but we're not going to include it because it's not part of the domain, as we saw over there. Even though it's greater than or equal to, that does not vibe with the bottom of the fraction. So we'll go from negative 7 to 7, not included, and then we'll go from 7 to infinity. And if you graph this on a graphing calculator, I think what you'll see is a vertical asymptote at 7, and you'll see the graph stop at negative 7. It will not have anything over there. Let's talk about the range of certain functions also. Range would be the output of functions. What comes out of these things? Really what we're starting to do is talking about one of the first topics we'll discuss in our class is the idea of end behavior. So when it comes to these problems, what we want to think about is the behavior of x to the fourth power as values of x get very, very large. Again, solving this without a graphing calculator can be kind of tricky. You've got to think about mind games for a minute. But what you should recognize about the term x to the fourth power and x squared, these are both even exponents. And what that means is they are never negative. Even exponents will always produce a positive answer because it'll either be negative times negative or positive times positive. So those terms can never be negative. In fact, the smallest thing they can be is 0. And if they are both 0, which I think happens when x is 0, it makes y equal to -1 because of this -1 that's attached on the end of it. I believe -1 is the smallest number that we can get out of this function, since x squared and x to the fourth are always positive numbers. So when it comes to the range of this problem, usually write with an r colon, the range of this problem is going to include -1, but -1 is the absolute left bound or bottom bound of this. And from there, it goes up to infinity and never stops. Since you can plug very large numbers of x in for these and get very large values out. 1 million to the fourth power is astronomical. So you go from -1 to infinity for that answer. Another thing to be familiar with is the behavior of exponential equations, like 100 to the x power. If you think about end behavior, as x approaches positive infinity, y also approaches positive infinity. If you start taking 100 to very large powers, y gets very large very fast. What's interesting about exponential equations, though, is if you start plugging in negative numbers, negative infinity, what you do is you get this whole 1 over 100 effect, which actually causes a fraction, which is very, very, very small. You could sketch a quick graph of this, too, which might help. It has an asymptotic behavior on the left side, but then it increases exponentially very quick like this. Every exponential equation basically looks like that graph. It's a little steeper or a little shallower, but they all have the same basic behavior. Y approaches 0, essentially is what's going on here. This is never 0. It approaches 0, but it's never actually 0. So 0 to infinity with round parentheses, that's the range in this problem. With question number 11, we got some more stuff to think about here. Again, you want to think about what you can get out of this thing. Let's consider that this, again, the square root here. The square root can only take in numbers that are 0 or more, and consequently, it only gives out numbers that are 0 or more. So the output of the square root part of this function is always positive. Or, well, I suppose there it's, how do I say this? Always greater than or equal to 0, like that. And from there, it's, well, actually, we can think about that even more. Not only is it always greater than or equal to 0, but look what's going on inside. X squared is always positive. And then you add 1 to it. So I think the smallest thing this fraction or this function can ever be is 2. And I'll tell you why. I think when x is equal to 0, then y is going to be the square root of 1 plus 1, which is 2. That's the smallest that I think we can ever get out of this particular function. So when it comes to the range, I'm going to start with 2. That's the absolute left bound. However, I think just like number 9 over on the left side, this is also just going to go to infinity, because as you plug in larger and larger and larger numbers for x, you get bigger and bigger numbers for y. So 2 to infinity with a round parenthesis is what we're looking for there. And this is the range, like that. You know, if you want to learn some college level symbols, not that they're difficult, you can say that y is in the set of 2 to infinity. I remember doing that a long time ago. That's what this symbol means. That's an epsilon in the set of. Pretty cool. Okay, let's look at some graphs. These are usually the easiest ones to look at. The graphs make these problems trivial, in my opinion. But again, what you want to do is do Terminator vision. You want to scan the graph from left to right and for domain, and then go from bottom to top for range and see what you're going to touch with this thing. So for number 12, when we scan it from left to right, we touch everything and we never stop. Looks kind of like we stop right there, but we don't. This graph keeps going on forever like this. So the domain in this problem is all real numbers, or if you want to use interval notation, negative infinity to positive infinity. The range in this problem is not all real numbers. It looks like it has a horizontal asymptote. I'm guessing that's at -2, just based on what I see on the graph. So I think the range is from -2 up to positive infinity, and I don't think we include -2 because it's an asymptote. So this goes from -2 to infinity, like this. That's what I think. For number 13, again, if you're thinking about this, there are two places where there are gaps. One in the domain, one in the range. The domain has a gap at -1. So our domain is going to be negative infinity all the way to -1, where we have that asymptote happen. And we're going to union that with the set of numbers from -1 to positive infinity, like this. Very cool. The range has kind of the exact same thing happening, but it's at +1 horizontal. This goes from negative infinity to +1. We're going to union that with the group from 1 to infinity. There you go. So there's a vertical asymptote at -1 and a horizontal asymptote at +1. And then we get these weird fun graphs. Calc is a lot of fun because we have to look at a lot of cool different things that we haven't thought about before. This is kind of like a diving board, I think about. Like it goes... It's oscillating as we go like this. So the way I'm reading this graph, I see kind of a dot right there at the very top. So I think the domain of this graph is 0 to infinity, and I'm putting a square bracket around the 0 because I believe it's included. The range, though, the range seems to vary from its absolute minimum point at, wow, I can't even read that. Is that supposed to be -0.5? I think it's supposed to be -0.5. And then the absolute top I see is up here at 1. Right there. I think that's what those numbers are supposed to be. So the range is from -0.5 to 1, and I am including both of those numbers because both those numbers are actually on the graph at some point, right here and right there. So there we go. Domain and range get used a lot more in calculus in more serious things. So be ready for those conversations. There's a lot of vocabulary that we just kind of sometimes throw out and just never explain what it is. I've always felt that way about domain and range, so there it is. All right, this video went a little longer than I want to, but I got a little long-winded, which happens. You'll learn that about me pretty quick. So, hey, I'm very proud of you guys for enrolling in this class. I can't wait to work with you in the fall. You did so great on this assignment, and I can't wait to see how far you go in this class, and I will see you in the next video.